Hello everyone, this is Manish Dixit. I'm an assistant professor and I, along with my colleague Dr. Sarel Lavy, who is a professor in the Department of Construction Science at Texas A&M University, going to present our research on the relationship of embodied energy and cost of buildings and building materials. So if you look at the buildings, we know that nearly half of global energy supply is consumed by buildings in their construction and operation. Nearly 16% of water annually. There are a variety of materials also consumed in their construction. As a result, there is carbon emission, there is pollution, and significant amount of waste. The effect of which, the adverse impact of which, we already see in growing number of radical weather events. So let's look at the life cycle energy model of a building. There are two major components of life cycle energy use of a building: life cycle embodied energy and life cycle operating energy. Embodied energy is consumed directly and indirectly in all products and processes, so like building materials, equipment, and construction and transportation processes that are used in constructing the building, whereas operating energy is used in HVAC, lighting, powering building appliances. So basically all of the energy that is used in operating the building is its operating energy. So if you look at the building construction, there are building envelope components, building interiors, there's structure, and then building systems. Each of this has materials involved and installation and construction processes involved. So there's a variety of products and processes that go inside the building. All of the energy that's consumed in manufacturing these products and carrying out these processes is called embodied energy. So the big question is, how do we measure? So there are tools to measure operating energy, but calculating embodied energy is challenging. So if you look at embodied energy calculation, some of the big challenges are that computing embodied energy requires significant time and resources, and the reason for that is the data is usually not available, or if it is available, it's incomplete, outdated, or inaccurate. So it's non-representative. In most cases, by the time you collect all the data, pre-process it, and calculate embodied energy of materials and processes, a number of years have passed, and that data that you have created is already years old now. In addition, you can quantify probably products and materials embodied energy easily, but some of the services like consulting services, engineering services, those are difficult to quantify. So there are a number of these challenges that make embodied energy calculation a daunting task. Previous research has shown that actually there may be a correlation between the cost of a product or a material or a building and its embodied energy. So the question is, what if we can predict embodied energy from cost data? And that's what the focus of this research is. The main goal is to look at embodied energy and cost relationship. So what we did, we quantified embodied energy using an input-output based hybrid model. This is one of the established approaches in the life cycle assessment field. I'm not going to go too much in detail of that model, but using that model, we conducted a case study of 5 university buildings at the material level and the building level, and then we analyzed the correlation of embodied energy and cost at the material and whole building levels. So here are the results that we found. If you look at the embodied energy and cost correlation at the whole building level, these are the 5 buildings, and you can see on the x-axis that there is a cost data, and then y-axis there's embodied energy data. So at the whole building level, you will see that the R-square value represents or shows that there is a strong and very strong and positive correlation between the total cost of the building and the total embodied energy of the building. When we look at the material level, you can see that 2 of the buildings showed strong and positive correlation, and so for building A and B, it was strong and very strong, and for three buildings, it was very strong correlation. If we combine all the buildings together with all their materials, so you can see on the right side with the green dots that you see the correlation is very strong. So at the material level, what we found that the correlation is strong positive to very strong positive. We also looked at the correlation for at the material level per unit of mass. So we looked at correlation of cost per kilogram of material and then embodied energy per kilogram of material. As you can see here that the correlation between the cost and embodied energy is really very strong and positive, both at all the materials level. So look at on the right side with blue dots and at individual building level. So the correlation is very strong to positive. So in conclusion, what we found that there is a strong to very strong positive correlation between embodied energy and cost of building materials and the buildings. We also performed simple linear regression analysis that further confirmed this correlation. We are not showing those results here to save the time, but these results are available in the paper. These results are also aligned with the previous research that has been conducted. What this shows that there is a potential for cost to be predictor of embodied energy. However, there may be more research needed, more data sets needed in order to conclude fully that we can predict embodied energy from the cost. Thank you very much. For any questions, please contact me or Dr. Lavy, and here is my contact information. Thank you.